Okay, I'm going to talk now about kind of a unique scenario about managing soils by calcium magnesium ratios. Okay, so we talked last time about how there's not a lot of need or effort or kind of consciousness about managing for calcium and magnesium. It's really about looking at pH and managing that, and then by default, calcium magnesium takes care of itself. That is true for Ohio soils for the most part. But there is a alternative school of thought that I actually never learned about when I was in grad school, but I want to kind of just make folks aware of it so you've got at least some understanding. That's what this talk is going to be about. So, this idea of soil management philosophies, there's typically considered maybe two or three main types out there. Um, there's the build-up and maintenance philosophy, which is what we've discussed last week with the tri-state fertilizer recommendations. And then a sufficiency level of available nutrients where you're applying essentially how much crop removal is. So really the tri-states kind of incorporate a little bit of, mostly based on build maintenance, but sufficiency level or the slant approach is also incorporated to some extent. And so, build maintenance is really feed the soil and the soil will feed the crops. Sufficiency level is more about just feeding the crops what they need. And then there's this third thing, which is BCSR, base cation saturation ratio. And base cation saturation ratio is when we're actually focusing management based on calcium, magnesium, and potassium. And in particular, oftentimes the ratio of calcium and magnesium. Okay. This management philosophy postulates that an ideal base saturation it's about 60 to 75% calcium, 10 to 20 magnesium, and then somewhere between 2 and 5 potassium. So we've already talked about the next few slides, but I just want to make sure everyone's on the same page about this. So what is base saturation? Well, base saturation is simply the percentage of basic cations, calcium, magnesium, potassium, and sodium, that occupy the exchange site. So it's calculated as base cations divided by the total CEC. Okay. And recall that we routinely estimate this in labs by summation, the sum of cations, okay? And so we can have base saturation, which is the total of base cations divided by CEC, but we can also have things like calcium base saturation or magnesium base saturation, potassium base saturation, and that's simply the base saturation, it's the percentage, it's really a ratio that's converted to a percentage by multiplying by 100. So it's calcium divided by CEC and then multiplied by 100. So calcium saturation is typically in Ohio soils anywhere between 50 and say 80, 85%. And recall that this is based on charge. So we do all that kind of funky math to figure out how many how many grams per mole of calcium, then we can convert that to a charge. So this is all based on charge, a charge basis. It's a milliequivalent per 100 grams of soil. Okay, so just kind of revisiting that. And then at this point we should understand that as base saturation increases, the dotted line, your pH is going to increase by default, and hydrogen saturation is going to decrease. So as your pH increases, the number of bases on that exchange site increase, the number of acidic cations, i.e. hydrogen and aluminum, iron, manganese, are all going to decrease. Okay. So let's talk a little bit about the history of this base cation saturation ratio, or BCSR. It's sometimes called soil balancing specifically, right? So this is not a new idea or a new concept. It really started in the 1800s or late 1800s. Searching for this kind of ideal calcium mag ratio in New Jersey in the 40s. Baer did some work looking at calcium and magnesium percentage, and then Really, it's William Albrecht. In the 40s to the 70s, William Albrecht was a University of Missouri soil scientist. Was the chair of the department. Made a big impact in terms of his writing and his thoughts. Kind of very forward-thinking, progressive, and he spent a long time looking at this stuff, and then at kind of towards the end of his career, wrote these manifestos of a bit, and that's what's pictured here. And it's talking about connecting soil fertility to plant nutrition, to animal nutrition or human nutrition, and so there's a lot of things written about this. Charles Walters in the 70s, with the publication of this popular magazine, Acres USA, you might have heard about. It's primarily a organic and sustainable ag magazine. Really popularized this idea of BCSR, and then really took these base saturations, which is what Albrecht talked about, 60 to 75, 10 to 20%, and turned them into ratios. So he just made it a calcium-magnesium ratio and talked about the ideal ratio, the ideal range of ratios. Okay. So Albrecht, there's been some written about this, and maybe a decade ago there was a review article that came out in Soil Science Society of America journal, and one of the take-home messages, they did a review of this, of Albrecht's work and other studies that have looked at calcium-magnesium ratios, and they stated that Albrecht concluded that it is important to maintain high calcium. Indeed, this was an observation that would eventually form the basis of his concept. It would seem, however, that the design and interpretation was flawed because what Albrecht did not properly account for were changes in pH. Okay, and so again, if we go back to this idea, as pH increases, your calcium and saturation is typically going to increase, your magnesium saturation to a certain extent, but calcium to a larger extent because it occupies a larger share of that exchange sites. Okay, so it's this idea of conflating. Did Albrecht conflate changes in pH for changes in calcium? So that's like a fundamental question that still hasn't been answered in a really satisfying way. Okay. Many farmers, especially organic farmers, contend that correcting soil imbalances will improve crop growth, weed problems, increase crop yield and quality, and overall profitability. The organic farming community especially has and thinks about soil cation balancing, or BCSR, as an important part of managing soils. And so it's not uncommon to find a fair number of organic farmers that subscribe to and manage soils based on calcium and magnesium ratios. Okay, earlier work has shown that maybe 60% of organic farmers in Ohio and Indiana thought about it and actively managed for it. It's true in New England and California as well. And then more recently, a project that I've been part of did a large comprehensive 4-state survey of organic farmers, organic corn farmers, and found that actually over half of them actively manage calcium and magnesium ratios. Okay. But here's the conundrum. In science, in soil science, this is a very contentious topic. Scientific community disregards this. It's not recommended by any land-grant university. But farmers and crop consultants still believe this works, okay? And so it's like this is has a really interesting human dimension component, because we say, well, why is it that land-grant universities have kind of disavowed this approach, said it doesn't work, but farmers are still using it, and crop consultants, there's whole crop consultants that have their whole practice based on calcium nutrition and thinking about calcium as kind of the main piece, the critical piece or the pivotal piece in terms of soil management. Okay, so getting that calcium balance right is all other things kind of fall into place. Um, so just to give you some perspective, what does previous research show? Okay, so a postdoc and I published an article a few years back when we looked at the peer-reviewed literature and tried to find everything that we could find in terms of looking at this kind of BCSR soil balancing perspective and what has been studied or what has been published on. We found, shockingly, 15 peer-reviewed studies, 7 field studies, and 8 greenhouse studies that showed, that reported on this. So this might sound like a lot, but for a concept that's been out and around since, for over 100 years, this is a really, really small number. And we even thought there might be kind of publication bias, where people will do experiments and they don't find anything and then they end up don't reporting it because the results aren't that interesting. This is a real thing that happens in science. It's called publication bias or whatever, where where results that don't show differences are more likely to not get published because the story isn't nearly as interesting, okay? And so we couldn't find evidence of that. We polled a bunch of people. There's a lot I could talk about. I'll move on for this, but suffice it to say that there was not much work that has been done and demonstrated through this peer review process. Okay, so the conclusions from previous research collectively, there was no ideal ratio where crop yields are maximized. Yields were not affected across a wide range of ratios. Some of this work actually happened. A fair amount of this work, these studies that I just mentioned, were published actually in Ohio. And interestingly, one of Albrecht's graduate students, E.O. McLean, did his PhD with William Albrecht in Missouri and then came here and started his career at Ohio State. And he was a well-known and well-regarded soil chemist. And he published a few papers showing that there was no, that this, soil balancing did not have an effect on crop yields in Ohio. And so, there's some interesting history there in terms of like Albrecht's one of his students coming to Ohio and not being able to replicate that information here. So, anyways, what we can do if we're applying a lot of calcium, we can spend a lot of money doing that and not having that provide essentially a good return on investment. So, sufficiency or build-up and maintenance approach is much more economical than BCSR, and that we should manage nutrients at an individual basis and not think of ratios of one versus the other. So this is like kind of the take-home from those limited number of studies. Okay. So we came into the scene and not. This is a project that's been it's in its 5th and final year now. We're trying to continue the work, but our funding source is essentially over, so that remains to be seen. But it's interesting from kind of like a philosophy of science perspective, because there's this wide gap between what the scientists say and believe and what the farmers do and believe, right? So there's not good communication, and there's this, there is this gap. So suffice it to say that this is really kind of what we were wanting to explore. Admittedly, we came into this project thinking that farmers were going to come and say, all we do is do calcium-magnesium ratios and nothing else. But we found nothing was further from the truth, especially organic farmers, where they think of managing calcium-magnesium as one piece of an entire suite of practices for soil health, right? So it gets how this is practiced in the real world is incredibly messy, and you can talk to 3 different people and get 3 different definitions. And in fact, we talked to much more than 3. We talked to dozens of people and got dozens of different answers. So we just had a heck of a time even defining what soil balancing was. A little bit maddening, but it does demonstrate that there's some paradigms, scientific paradigms that are really reductionistic, and they don't, in a neat and tidy way, fall into like how farmers think about things, how they come up with their belief system, what they understand and come to know that works, what doesn't work, what they value, etc. So there's a lot of facets to this project that we won't really spend a lot of time on. I'm just showing you a couple soil test reports to see that despite university recs that don't need to manage calcium magnesium ratios, well, here's percent cation saturation of K, mag, and calcium right here. So it's on, this is a major lab in Fort Wayne, ENR Labs. Another major lab, Spectrum Analytic in Washington Courthouse, Ohio, again has these base saturation numbers. So it's commonly reported in soil test results because people want them. They want to see that information, okay? So for better or for worse. So again, tri-states, here's really kind of if you pull the tri-states and you read that section on calcium magnesium, these are really the take-home points. There's exchangeable calcium, should be over 200 ppm. After that, no response should be expected. That's, again, a low bar. For magnesium, minimum 50 part per million, so again, a very low bar. Most plants grow well over a wide range of soils, and again, this is work, the tri-states that were based on looking at the work that was done in Ohio, not extensive work, but a fair amount of work showing that regardless of the calcium magnesium ratio, crops yielded reasonably well. So the only thing the tri-states does say, and it's unclear where this comes from, but they say that you should have at least 1-to-1 calcium magnesium ratio, and that would be very difficult. If you're maintaining pH, it would be very difficult to get that. It would typically, there's much more calcium than magnesium in soil, so a 1-to-1 ratio is a very low bar, and for magnesium, a 2-to-1 ratio, magnesium to potassium. Both of these, almost always occur. So you'd have to do something your soils would have to be very unique or have very unique management for these two things, these two criteria not to be satisfied. Or really, we could talk about these first, second, and then third or fourth and fifth criteria to not be satisfied. Okay, so I we can compare the different philosophies or soil balancing versus SLAN, sufficiency level of nutrients. Here's calcium, magnesium, potassium, this ribbon, and then this is extractable cations versus CECs. So as your soils go from sandy to a clay soil, and a very heavy clay, here's that ribbon of at a pH of 7, what calcium 60 to 75% would represent in this band. For magnesium, this is 10 to 20%, and for potassium, this is 2 to 5%. So you can see that most of the time, we're well, like these dashed lines, I should say, 200 part per million for calcium for tri-state, 50 for magnesium. And then here's this dashed line based on different CECs for potassium. Okay, so most of the time, calcium, calcium magnesium, the base saturation that's prescribed by soil balancing is much higher than what the tri-states say. And that means that, that's fine and all, but if we, say, have a CEC of 20 soil, CEC milliequivalent per 100 gram, and our calcium saturation is down here, well, it's going to require quite a bit of material to bring it up into range, okay? And likewise, if we're up here, we might have to, add calcium to drive the magnesium down, et cetera, et cetera. So the question is like, how much, sometimes these two recommendations are fully aligned, but when they're not, it can be expensive. And so that's the justification, or that's some of the main drawback of managing for soil balancing, because you can just spend a lot of money in calcium products, primarily gypsum and even lime. That might not be necessary. Okay, here's just a figure legend to describe that figure. Okay, so we'll move on with that. Okay, so let's talk a teeny bit about, I don't want to spend too much time on soil balancing, but talk a teeny bit about what's behind this. Okay, so this is our working hypothesis, and aggregates, of course, are key to soil physical structure. We'll talk more about this later when we get into soil health, but suffice it to say, it's like primary particles form together to make sub-microaggregates, to make microaggregates that all form together to make macro. And these aggregates actually form and make up the porosity of the soil and really hold the mineral together. It's that organic material that's interfacing that mineral material, the sand, silt, and clay, and creating that structure that's really important for air and water exchange. Okay. So the idea then is that calcium has a smaller hydration radius or hydrated radius than magnesium, and sodium has a much larger hydrated radius than both. And so with sodium, we get a kind of a dispersion of soil. We talked about this in the sodic soils, where we get destruction of aggregate structure and kind of, it's just easier for me to say, like, imagine you take your soil and you put it in a blender and you blend it in the solution, and then you let that dry and you destroy all your pore structure, and then it just turns into this like slop, and then it turns into concrete when it hardens, right? And comparing and contrasting, again, this is more theoretical, but the idea is that calcium will help essentially form clay minerals together, so it will help attract, and this is what we call flocculate. So it's actually causing them to stick together and aggregate, versus the magnesium, which is causing them to disperse and reduce that kind of aggregate structure. Okay, so we know from chemistry that calcium is better for structure than magnesium. Here's the rank order of calcium, magnesium, potassium, and sodium. Sodium is a very dispersive cation, and because of that, sodic soils can often be very problematic. And one of the reasons, we know that we can go out and apply for, and this happens in arid regions that have had poor salt management, but in really salt-affected soils, you can apply gypsum, calcium sulfate, or some other calcium product, lime even, at really high rates and drive that magnesium off. And that's kind of what is done in the soil balancing context, but to a lesser extent. We know that if we drive sodium off, we get better soil structure. Drive sodium off with calcium. Calcium will help give us better structure. What's really unclear at this point is if the same phenomenon is true for magnesium. Okay, so this is doing a little bit of a deep dive into some of the theory, but it's just, for those that are interested, it's good to know some of this. Okay, so in practice, managing calcium-magnesium ratios, two products are typically used: high-cal lime, so that's lime without magnesium, and then gypsum. So again, lime raises pH. The effects of crop productivity are well documented. Gypsum does not raise pH. And then, I just showed you in the sulfur section that applying a lot, most of those trials were gypsum, and then they had really no effect on yields, at least. So that's, as one measurement. So again, for sulfur nutrition, we're typically at 20 to 30 pounds per acre. But when we're applying, say, a ton of gypsum, it can be, the application rates are, say, 2,000 to 4,000 pounds per acre. And if we can assume that maybe 20% of that is, 16% of that is sulfur, it's still, in the hundreds of pounds. It's a whole order of magnitude different than what a crop will actually need. So, okay, so, one of the underlying questions is, when we add lime, we always do two things. We always raise pH and we always add calcium. Okay, so that's every time we lime the soil. So some of the questions that we have are there additional benefits from lime that are not related to increasing pH? Is calcium providing any additional benefits that we've all along assumed that it's just a lime effect? And we can also ask the question, are the effects of gypsum that we see, calcium sulfate, a sulfur response, or is it a soil conditioning response? So when we add gypsum, of course, we can add it for the calcium, we can add it for the sulfur, we can add it for both. Okay, when we add it for sulfur, we can add very low rates, but when we add it for the calcium, it's usually in the tonnage, kind of, 2,000, 3,000, 4,000, 5,000 pounds. So it's a huge, it's much, much more from a soil conditioning or calcium perspective. Our working hypothesis is that applying lime to soil increases nutrient availability, which increases soil biological activity and improves crop growth. When we apply gypsum, our hypothesis is that it increases soil aggregation and physical structure, which increases root growth, water gas exchange, soil biological activity, which improves the crop. This is a very well-established thing. We know lime works. There's nothing, we've talked about this. That's very clear. There's still a lot of, the jury's still out to some extent. And I think, from my perspective, the effect of lime is very well established because it's very, very consistent. Applying gypsum, we're not getting nearly as consistent results, if we get any results at all. And that's partly why this is still, quote-unquote, a theory, and this is, quote-unquote, established doctrine. Okay. So anyways, we've done 5 years now of a fair amount of experimentation in Ohio, field trials, both on-station and on-farm greenhouse studies. We have not found, unfortunately, much evidence of really drastically different soil and crop properties after manipulating the calcium-magnesium ratios in different places. It's really hard for me to believe that there's 50% of organic growers are practicing this and they're not seeing benefits. So we're trying to understand what some of those benefits are. I think it's possible that there could be increases in pH that is getting attributed to calcium saturation, but it's really unclear. So we're still hoping to kind of continue down this path. We've been, maybe ridiculed a bit by other soil scientists saying, why are you guys working on this? This is crazy. Everyone knows this doesn't work. We did this work 40, 50 years ago as a scientific community and proved it. So why are you, going back and rehashing it now? And I would say that, we need to, if we want to engage with the people that are doing this and learn from them and, help them manage their soils better, we really need to try to figure out what benefits, if any, are coming from this. So anyways, that's the project. And more important than the project itself is just kind of the overall view. There's plenty more to learn about this. And, we could do a deeper dive, of course, but I think 30 minutes is sufficient. So I'm going to end there. If you want more information, I can provide a link. You can search for offer.osu.edu, and that will provide some more context, some more information about this. Okay, thanks.